So last time we discussed about the oxidation, that how we grow oxide on silicon surface and what are different parameters that actually affect the oxidation rate and how we can change the rate of the oxidation. So today we are continuing with oxidation. So we'll be discussing about the stress in the oxidation. There are two types of stresses actually. One we call as the residual stress. In the oxide layer, you know that the residual stress is actually due to the difference in the thermal coefficient of expansion. That you know that we grow oxide at very high temperature, maybe at 1000 or 1100 or even more than that temperature. So when you move, when you let the wafer to cool down at such high temperature, so during that time, due to the difference in the TCE, that is thermal coefficient of expansion. The thermal coefficient of expansion of silicon is much different from silicon dioxide. Silicon dioxide is 5 times higher than that of silicon. So that's why due to TCE, where should I get it? So it's actually TCE, that is thermal coefficient of expansion. The change in the thermal coefficient of expansion actually causes that residual stress. So when you cool down or when you heat up your wafer, at that time this stress should come into account, because the silicon oxide has got 5 times, it actually cools down at much higher temperature, 5 times high thermal coefficient of expansion as compared to silicon. So due to that difference, there would be a residual stress. Second type of stress is actually at the interface of silicon and silicon dioxide. That is, at the interface, actually, you know that the volume of silicon is actually different from the volume of silicon dioxide. For a specific volume of silicon, for a specific consumed value of silicon, I would say that more than 2 times of silicon dioxide volume is created or is actually generated. So due to that volume difference, because at the interface the volume of the silicon dioxide is much higher, that is approximately 2 times as compared to what volume of silicon has been consumed. So due to that volume, because if this much silicon has been consumed, 2 times of that, this much silicon dioxide has been produced. So due to that difference in volume, it needs to adjust that volume. So that change of volume, that difference of volume actually causes a stress at the interface of silicon and silicon dioxide. Because it's not like that, you know that it's not that silicon, the same amount of silicon is converted to silicon dioxide, it's not like that. Silicon needs to get reacted with oxide, with oxidant to produce silicon dioxide. So that's why the amount of silicon that is consumed, that is not exactly equal to the volume of the silicon dioxide that is produced. That makes sense, that silicon dioxide volume should be at least 2 times of silicon. So that's why that difference of volume causes a stress at the interface of silicon and silicon dioxide. So these are the 2 types of stresses that you will always keep in mind. One is the residual stress due to the difference in thermal coefficient of expansion, and the other one is at the interface due to the difference in the volume consumed of the silicon and the volume produced of the silicon dioxide. Okay, the second thing is actually about the dopant, or we call it as impurity. The dopants or the impurities at the surface of silicon. I'm talking about the surface of silicon. If you remember, we have silicon. If this is the surface of silicon, this is silicon dioxide that would be actually grown. We are growing the oxide, we are not actually depositing, because I told you that we can deposit as well, but right now we are discussing about growing, and for that we need silicon substrate. So at the surface, this is the surface of silicon. It will also keep moving down as we grow more and more silicon dioxide. So at the surface of silicon, the impurity concentration, or we call the dopant concentration, that does not remain constant during the oxide growth. So the change in the impurity concentration or the change in the dopant concentration, that's what we call as the dopant redistribution. We call it as the dopant redistribution. Okay, so I said that the dopant concentration or the impurity concentration at the surface of silicon, that does not remain constant during the oxidation process. So what should be the reasons, what should be the causes that make this dopant redistribution at the surface? So, yes? Sorry. Okay, so these are the three reasons actually that has been put on the slide as well. First one, that is named as the segregation coefficient. The segregation coefficient of that particular dopant or impurity. How you define the segregation coefficient? We denoted by M, that is actually equal to the equilibrium concentration of impurity in silicon, the ratio of that to the equilibrium concentration of that same impurity in silicon dioxide. Okay, the ratio of that specific dopant or impurity in silicon and silicon dioxide, that is named as the segregation coefficient of that dopant. That is one of the parameters that causes this redistribution of dopant at the silicon surface. So how actually that causes? I'm saying that if I'm saying that M is less than 1, what does that mean? If the segregation coefficient for any particular dopant like boron is less than 1, is less than 1 means that that particular dopant or impurity should be more in oxide as compared to in silicon. That's why M is less than 1 means denominator is higher as compared to the numerator. Okay, if we have such any dopant, if we have such a dopant that in which case the segregation coefficient for that dopant is less than 1, so it means that its concentration, the concentration of that particular impurity or dopant would be higher in silicon dioxide as compared to in silicon. So it means that more of the dopant or impurities are becoming accommodated inside the silicon dioxide. So now the concentration will go down. In silicon, the impurity will go down because more of it is actually being accommodated by silicon dioxide. Now I hope that after this example you have understood what this segregation coefficient means. Segregation coefficient means that if the equilibrium, if the that particular dopant has got M is greater than 1. Greater than 1 means that its equilibrium concentration is higher in silicon as compared to silicon dioxide. If this is the case, like in case of phosphorus, in case of gallium, so we have M is greater than 1. These two things, for this M is greater than 1, this is M is less than 1. So every dopant has its specific properties, that is the segregation coefficient. So if in case of phosphorus M is greater than 1, it means that in this case the dopant or the impurity would be higher in silicon as compared to in silicon dioxide. So as we grow more and more and more silicon dioxide, as we have seen that M is greater than 1 means that this particular dopant is not capable of getting itself accommodated in silicon dioxide as compared to silicon. So as we grow more and more oxide, more and more of the dopant or impurity will be inside the silicon. Okay, so that's what we say that the concentration of that dopant is redistributed at the surface due to this one parameter. The second parameter is about the diffusivity in the silicon dioxide of that particular dopant. That it may depend that if that particular dopant has got more diffusion in oxide layer. So in that case, what will happen? That due to the like boron is smaller atoms, it can diffuse easily. If it diffuses through the oxide layer, and it can escape the layers. In that case, again, the concentration will go down at the surface. The dopant will redistribute, and the dopant will be smaller than that. So the diffusivity This, because every particular dopant will have its specific diffusion rate. So the second parameter that we will have to keep in mind that can affect the redistribution of that particular dopant is actually the diffusivity of that particular dopant in oxide layer. And third and the last reason, it's actually the rate of silicon and silicon dioxide, the rate of oxidation at the surface actually. You know that when we grow oxide layer, if I grow oxide layer more, so if you remember in the last lecture, this surface, the silicon dioxide surface, it remains constant or it changes? Do you remember? It changes. It goes down inside the silicon. As more and more oxide grows, actually it consumes a particular amount of silicon because it's consuming silicon and oxide to grow oxide layer. So if we grow more, so a particular amount of silicon is added and a particular amount of oxide is added. So this is the total thickness now. Okay, so that silicon and silicon dioxide interface, that also changes actually. So the speed or the rate actually with which that layer is moving, that also contributes towards the redistribution. Because if it's faster rate, so it means that there is a faster consumption of silicon dioxide. I'll explain it in the terms that if we consume m is equal to 1, if we say that is segregation, if we are assuming that the segregation coefficient does not play any role, means the same amount of dopant or impurity can accommodate in silicon as in silicon dioxide. So it means segregation coefficient will not play any role in that particular case. If we take this case, in that case, you know that the volume of oxide is 2 times greater than silicon, right? The volume, if let's suppose that 0.02 micrometer cube is actually the volume of silicon that is consumed. So this volume of silicon dioxide that is produced would be 2 times of that. That is 0.04 micrometer cube. Yes.
So does the growth rate of silicon dioxide also depend on dopant concentration?
Sorry.
Or is that negligible? So if I have a particular concentration of a certain dopant, does that affect the growth rate?
Yes. Last time we discussed this thing that dopant concentration also affects the growth rate.
So we got this really nasty differential equation describing how the concentration changes?
Yes. Last time we discussed about the Dale-Groves equation. I believe you were not there. But yes, the dopant is one of the causes actually that can affect, in addition to there are very other parameters as well. Actually basic, the 3 Dale-Groves equation that takes into account only 3 basic parameters, that is temperature, that is diffusion, and that is reaction rate. You have seen F1, F2 and F3, there were 3 fluxes. But yes, the dopant actually plays an important role, especially in case of polysilicon. In polysilicon, the higher, even in crystalline silicon, the higher the dopant rate or the lower the dopant rate, that will affect the oxidation rate actually. Okay, so I was giving you an example that if m is equal to 1, in that case I am saying that there is no difference in the segregation coefficient is equal to 1, means the same amount of impurity concentration is accommodated in silicon as in silicon dioxide. In that case, just think that when 0.02 micrometer cube of silicon is consumed, 0.04 micrometer cube of silicon dioxide is created or is generated. So in that case, it means because 2 times of volume of silicon dioxide is generated, so it needs 2 times of that impurity concentration or dopant concentration as compared to what was in silicon. Am I right? If m is equal to 1, means that the equilibrium concentration is the same in both silicon and silicon dioxide. But due to the volume, if in 1 micrometer cube, if we have 10 impurity atoms in 2 micrometer cube, we should have 20 because the equilibrium is the same. In 30 micrometer cube, we should have 30, or in 3 micrometer we should have 30. So assuming m is equal to 1, due to the change in the volume, because more oxide has got 2 times the volume as compared to the silicon that is consumed. So it means even if the segregation coefficient does not play any important role, even in that case, that impurity concentration will go down, because in oxide it needs an extra same amount of impurity or dopant concentration to make silicon dioxide. If you are still confused, let's suppose I have silicon that is 1 micrometer cube. It's too much actually, that volume is too much. I should say it's 1 nanometer cube. And silicon dioxide, as I told you, when this silicon is consumed, how much silicon dioxide should be produced? 2 times. 2 nanometer cubes. So when this silicon is consumed, this silicon dioxide is produced. So if this silicon was having 10, the concentration of particular dopant, whatever we're talking about, is 10 in this silicon. If the segregation coefficient is equal to 1, I mean that is linear, the same ratio. In 1 nanometer cube it should be 10, in 2 nanometer cube it should be 20. Because I'm assuming that m is equal to 1. If m is equal to less than 1, it means it should be higher than 20, because silicon dioxide can accommodate more concentration. If m is equal to greater than 1, yes, that in that case I would say it should be less than 20. But I'm assuming that m is equal to 1 because I'm discussing the third parameter. So it needs 20. When it needs 20, it means it's not taking, the silicon is not losing 10, but it's losing actually 20. The overall loss of the impurity is actually 20, so it means that at the surface of silicon, the concentration will go down. So in this way, these are the 3 parameters that can affect the dopant concentration, that we call as the dopant redistribution. So in other words, we will say that the dopant concentration at the silicon surface keeps changing during oxidation. That does not remain constant, and we call this phenomena as dopant redistribution. What are the causes? We have discussed.
So I have a question.
Yes.
So you are using 2 terms, dopant and impurity together.
Oh.
So I'm just confusing. So the impurity comes from where is the dopant?
Yeah, that's why I'm saying that actually dopant is also an impurity, but that is, you can say, beneficial impurity. Dopant is also considered as an impurity.
So that comes from some naturally, not we do not artificially.
Yes, when we that's why I say that I'm using dopant and impurity as alternative words actually, because dopant is actually, I mean, if you have a silicon crystal, anything other than silicon will actually be considered as an impurity. But if we have introduced that impurity intentionally, we say that it has been doped by this thing.
Right.
So dopant is also a beneficial impurity that has been introduced intentionally. So that's why I'm saying dopant, or sometimes I say impurities, because dopant is also an impurity. I mean, in silicon crystal, anything other than silicon, if instead of silicon atom I have some other atom, so it means that is an impurity in there.
Okay. So in this process,
yeah, everything relates to dopant, or you can say everything is actually about the impurity. They are the same thing. So the dopant or the impurity, I'm using those alternative terms actually. Okay, so oxidation of other materials. Up till now we have discussed about the oxidation of silicon. Now we are going to talk about the oxidation, but as I told you yesterday that we are discussing oxidation means thermally grown oxidation. We are still talking about thermally grown. We are not talking about the deposition. Okay, so even in this oxidation of other material, we are still talking about the thermally grown oxidation. And when we are talking about the thermally grown, we need silicon in there. If we don't have the silicon, you cannot grow silicon dioxide. You can deposit silicon dioxide, but you cannot grow it, because in order to grow it, you need silicon so that it can react with oxide to grow silicon dioxide. Okay, so oxidation of polysilicon. You know what is polysilicon?
Polycrystalline silicon?
Yeah, it's actually the polycrystalline. So if I talk about the crystalline structure, how a crystalline silicon differs from polysilicon.
Polysilicon has only groups of kind of like grains which are aligned in.
Okay, in crystalline structure, we say that we have long range orders of crystalline forms.
The cubic structure repeats throughout the silicon in crystalline, but
Yes.
in poly it does in only certain directions, then in others it changes its type.
Yes, so you have short range of crystalline forms at specific area. This is in order actually, in this part it's in order, in the other part. So that is actually the polysilicon, that you have in specific parts you have actually crystalline forms, but that does not run, that order does not keep itself throughout that layer, so that's why that is not purely crystalline. So at the boundary where one format or where one format differs from the other format inside the polycrystalline, that is named as grain boundary. You may have heard about that. Okay, that actually differentiate two parts of a crystalline form. So if we are going to thermally oxide polysilicon, I say that the oxidation rate for crystalline silicon is lower as compared to the polysilicon. So polysilicon gives you a higher rate as compared to the crystalline silicon. This is due to, because as I told you that at the grain boundaries there would be a stress. At the grain boundaries, this part and this part of silicon in a polysilicon, they would be in different formats, so there should be stress at every grain boundaries. So due to the stress at the grain boundaries, the diffusion is always higher, and diffusion is also one of the parameters that increases the rate of oxidation. So it means that the oxidation rate would be higher in case of polysilicon as compared to a crystalline silicon.
Why would you want to oxidize polysilicon?
It depends upon our application. That's why I say that the crystalline silicon, the quality of crystalline silicon would always be better as compared to the polysilicon oxide. But polysilicon oxide, let's suppose if I need a sacrificial layer, I would. I'm not concerned with the quality of the oxide. Even in case of sacrificial layer of oxide, I would recommend, or I would like to have an oxide layer that is easy to be etched away. Means it should not be that crystalline. So I don't need a better quality because I need to remove it later on. So that's why it depends upon our application, that what type of oxide layer we need. But at least you should know that if we have a silicon surface or if we have a polysilicon surface, how the reaction rate would actually differ from each other. Secondly, the quality of oxide depends greatly on the physical structure and impurities in original polysilicon. The quality is that it depends on the roughness of the surface of polysilicon. If you have got a very smooth surface of polysilicon, in that case the quality of the grown oxide would be better as compared to a rough surface. If we have a rough surface, so it means it's the physical structure that actually counts towards the quality of silicon dioxide grown on a polysilicon. If you have got a rough surface, the oxide grown on that polysilicon, that would not be of good quality. So if that is not of good quality, it means that its breakdown voltage would be lower as compared to a good quality. So if we want some surface that has got lower breakdown voltage, we need a rough surface, because we don't want a very high quality silicon dioxide with a very high breakdown voltage. So that's where that actually answers your question, that why do we need a lower quality. If maybe we in our application, I need that oxide layer with a lower breakdown voltage. So if I need a low breakdown voltage, I don't need very high quality of silicon dioxide. So in that case, I'll be having a rough surface of polysilicon. And if I need a better quality, I can actually have a smooth surface as compared to a rough surface of polysilicon. What are the uses? Gate electrodes, passivation layer, and we discussed in the last lecture as well that there are other uses as well of silicon dioxide, like masking, sacrificial layer, or some other benefits. Oxidation of silicon nitride. If we have got a silicon nitride, can we oxide it just like a silicon? Can we thermally grow silicon? Yes, it's not like the silicon, but we can grow. A very, very thin layer of oxide can be grown on this silicon nitride surface. So you can form oxynitride, but that would be very thin, maybe not more than 30 nanometer. So that's why a few monolayers of nitride will oxidize, means some of the nitride will be replaced by oxide. So as it says, self-limited by the ability of oxidants to diffuse through the resulting oxynitride film. So if you have listened to the last lecture, you should understand this statement, that I told you that there is one that is named as diffusion limited reaction, one that is named as reaction rate limited process. So this is self-limited. What is the how it is limited here? Ability of oxidants to diffuse through. So it means due to that diffusion process, because it's very hard for the oxidant to diffuse through the oxynitride layer, that is silicon nitride layer, after a few nanometers, it's very difficult for the oxidant to diffuse through, so it's limited after that. So you cannot grow thick layer, but very thin layer can be grown. Yes.
So what does silicon nitride turn into when you oxidize it?
Oh, silicon nitride would be actually, that is oxynitride.
Oxynitride.
Yeah, that is oxynitride that is actually formed when you oxide silicon nitride. But you cannot grow thick layer. In that case, it would be only a very few nanometers of oxide layer that can be grown on the silicon nitride.
What use is it?
It can be sometimes it can be useful. It depends, again, it depends upon the application, that whether we have. You can see that in the next 3 to 4 lines you will come to see what are the benefits or the drawbacks. That first of all, if I want to remove the nitride and there is an oxynitride layer on the top of that nitride, so it means that that oxynitride will not permit to remove that nitride if I want to. So that is a drawback. But at the same time, if in my application I want to mask my nitride, I can use that oxynitride to grow. So here that the use comes in. That oxynitride does not permit the nitride under it to etch away. It actually behaves like a mask.
So it's a passivation layer.
Yeah, it's a passivation layer. So if I want to use it as a mask, I can. But if I was intending to remove the nitride, in that case, this oxynitride layer would actually provide a hindrance, would actually be reluctance to remove that nitride layer. So what should we do in that case? That is, for example, in order to remove the nitride layer, phosphoric acid at high temperature is used. At the temperature of 90 to 95 degree, phosphoric acid is used to remove the silicon nitride. But the oxynitride will not be, that oxygen layer, that will not be removed or etched away by this phosphoric acid. So we will have to remove that oxide layer before we actually can etch the nitride. So in order to remove that oxide layer at the top, that is very thin layer, what we can do, that we can actually dip it into buffered BHF, that is the buffered hydrofluoric acid, that is used to etch the silicon dioxide. So we can dip it in HF solution, it will remove the oxide layer, and after that we can expose it to phosphoric acid at 90 to 95 degrees centigrade, so that now we can remove the silicon nitride. So this way we can remove it if we want to.
So if I understand that correctly, hydrofluoric acid removes oxynitride, but phosphoric acid does not.
Not oxynitride, it's actually oxide. Yes, you got it right. That HF is used to remove oxide, but phosphoric acid does not remove oxide. Phosphoric acid, boiling phosphoric acid removes the nitride. But if we have the oxide layer, a thin oxide layer at the top of nitride, we name it as oxynitride because we have nitride and oxide at the top. So that oxide needs to be removed by dipping in HF. And for that case, you should know exactly what is the thickness of oxide and what is the H rate of the solution that you are using.
Is oxynitride a better insulator than either the oxide or the nitride?
Sorry?
Is oxynitride a better insulator than only an oxide or only a nitride?
For this thing, we should know about the dielectric constant of oxynitride or nitride or oxide. But I have so far as I know about nitride and oxide is better than nitride. Nitride is actually the second option for in industry after oxide, but oxide is still better than silicon nitride. Yes. But in some cases, sometimes, as I told you, that in some cases silicon nitride comes into play. It's better option as compared to silicon dioxide. It depends again on our process, that what protocol we are following. Let's suppose if we are following the protocol where we are using the HF. So in HF, if we are masking something, if we are using it oxide as the passivation layer, and in case of HF process, oxide layer cannot be used as the mask. So we will go with the silicon nitride. So in that case, silicon nitride, because silicon nitride is not affected by HF, but silicon dioxide is removed by HF. So depending upon the application, sometimes we introduce silicon nitride instead of silicon dioxide as a passivation layer or as a hard mask.
So can we, in general, think of oxynitride as an oxide in most of its properties?
Oxynitride is actually when you have silicon nitride and then you put it in, then you put that wafer that has the silicon and on top has silicon nitride. You put it in at high temperature in an oxidizing ambient.
I understand, but as far as its properties are concerned, does it behave mostly like an oxide in that you can remove it with HF, it's resistive, it's a passivation layer, etc.?
Yes, that's actually silicon dioxide, that is oxide at the top, because in oxynitride at the top you have oxide and then you have got the nitride. So it's weird. In order to start with, we need to remove the oxide.
So it's an oxide.
Yes, it's oxide. Then the silicon nitride. Okay, so now we talk about the oxidation systems. Up till now we have discussed about the oxidation, that what are the different parameters that control the oxidation rate and how we can grow the oxidation. If there is some other material than silicon, what would be the oxidation process effect in that case. Now we are going to talk about the oxidation systems, that how we actually grow the oxide on the silicon surface. So in oxidation system, you should know about the furnace. That what is the furnace? That is a quartz tube that can be heated at very high temperature, more than 1000 degrees centigrade. So that quartz tube is named as a furnace. Okay, so as you can see, this thing, that it's a quartz tube, and the oxidant, that may be the oxygen or that may be the steam, that comes in, and at that high temperature, it that oxidant reacts with the silicon surface. The wafers are inside, and one thing that is missing here may be that we have the exhaust as well with that tube, the furnace, the quartz tube, because you know that oxidant comes in at the same time. If there's some byproducts or even that ambient oxygen, that needs to go outside as well. So there is an exhaust pipe as well. We will see this thing in the lab. Tomorrow we are going to work with this horizontal furnace. So and I mean in this week, in both the labs in this week, we will be doing using this oxidation furnace. That is, there are different types of furnaces. That horizontal furnaces that were previously used, but later in mid-80s, after mid-80s, they were replaced by the vertical furnaces. Now the horizontal furnace looks like this actually. In industry we have only a single layer, but in industry we have actually mostly 4 stacks of the horizontal furnaces, and you see these are actually the furnaces. These are the openings to the furnaces. Okay, these are the openings to the furnaces, and these are the wafers that actually are existing vertically, that are lying vertically on the quartz board. There is a board. Okay, so that board is actually pushed inside the furnace for specific time. The furnace is already at high temperature, and after specific time it is taken outside. In this case, it's automated. That is, these all four automated in a way that all these four would be actually pushed inside by a single robotic arm. But here in the lab, we will push it inside manually, and we will push it outside manually as well. Okay. Now you can see that in the horizontal furnace, that actually lies horizontally. Why I say that after mid 80s it has been replaced by vertical furnaces? What are the benefits of vertical furnaces over the horizontal furnaces? We'll talk about that. Actually, the first thing is actually in horizontal furnace, if you see the horizontal furnace, the 3-zone furnace, and that heating system is actually upper and at the lower side. So that actually heats the wafer from one end to the other end. So you know that you are not heating the wafer at one time. It needs to move across the wafer surface because you are heating it vertically. So that's why in horizontal furnace, the cross wafer oxide uniformity, we may have not a very uniform oxide layer, because the distribution of the heat distribution is not uniform across the wafer surface. Because initially maybe this lower part was at high temperature, but this upper part of the wafer is still waiting for the heat to move forward. So that's why when this was at high temperature, the lower half of the wafer, the upper half of the wafer is not at that temperature initially. So it means that the lower part is getting more silicon dioxide or oxidation rate as compared to the upper part. So that's why the overall profile of the wafer will not be uniform. You won't be having a uniform oxide layer on the wafer surface due to the non-uniform distribution of heat. So in case of vertical wafers, you place every wafer in a specific slot. So when wafer is heated from this part, it means that on the surface of the wafer, the temperature is uniform. There should not be any non-uniformity in the oxide layer. So you got the point that in oxidation the wafer is this way in the horizontal furnace. So when it is in this way, it means that heat needs to transfer from the lower end to the upper top. So maybe at specific point, this part would be high temperature, this part would be at low temperature. But if it is in vertical furnace, it's always lying down in a specific slot. So when I heat it from this part, it means that all the surface is getting the heat uniformly. So that's why there would be uniform oxide layer on the wafer surface. Secondly, improved particle control. In case of vertical furnace, we have a more automated system actually, because automatically it picks the wafer and it places the wafer back. So we are not taking it out until it's oxidized to a specific temperature, to a specific thickness actually. So due to the automation of vertical system, it's more contamination controlled process. In that case, because you are not taking it out of the system, you're not exposing it to the air, so there are less chances that there will be impurity or the particles on the wafer. So due to that automation, there is a better control of the particle or contamination in case of vertical furnace. Secondly, now this vertical furnace is used for thick layer oxide. For thick layer of oxide, so it means that it needs to be inside the furnace at for a much longer periods of time. For thick layer, you need to be put it inside a furnace for greater period of time. So when you're putting it inside the furnace for greater period, so it means your throughput is actually going down. So in order to increase the throughput, the vertical furnaces are always processed in the form of large batches, maybe more than a 50, 150 or 200 wafers at one time. So they put a large batch of wafers inside, because inside the furnace, if you're putting one wafer, if you're putting 100 wafers, it will take the same time to grow a specific amount of time, specific amount of oxide on the surface. So that's why, due to the low throughput, we always deal with large batches for the vertical furnace. And secondly, these days actually these vertical furnaces, because as I told you that it has its drawbacks as well, low throughput was a drawback, that has been compensated actually by processing large batches, so that if you process large batch, you can compensate that low throughput. But recently that vertical furnace has also been replaced, but still we are using vertical furnaces in industries, but that has been replaced by rapid thermal processor, RTP. So as the name shows, what is the rapid thermal processor? Okay, this is showing you that exactly the same horizontal furnace that we'll be using inside the clean room tomorrow, and you can see that the temperature distribution is not uniform across the wafer actually, because as I told you that it starts heating from one end to the other end, so that's why the temperature is not uniform. So that's why we won't be having uniform thickness of oxide on the wafer. So you don't have a uniform profile. And this is the vertical oxidation furnace. Okay, we were talking about rapid thermal processor, that is RTP.
So before going first, so the furnace, it's like we can use both wet oxygen and dry oxygen.
Yes, in any furnace, it depends on what is the ambient, what is the oxidant agent actually. That's why I'm using oxidant term instead of oxygen or instead of steam. So we can use both. What we'll be using tomorrow in the lab, that would be dry oxide. So in dry oxidation, what will be the input, what will be the oxidant, that would be oxygen, not the steam or the water vapors. But you know that the quality would be better, but what would be the problem with the dry oxidation? What is the limitation of the dry oxidation? That is actually the thickness. That is the oxidation rate. The oxidation is very low, so you cannot grow a thick layer of oxide. If you want to grow 1 micron, you cannot do it with dry oxidation. You will have to go to wet oxidation. Okay, so but yes, he is right that whether it's the horizontal, whether it's a vertical furnace, you can use both dry or the wet oxidation. Okay, rapid thermal processing. Before we discussed with, it's actually the most recent technology that has replaced even vertical furnace, because I told you that in the vertical furnaces the problem is with the throughput, because it takes much time to heat the wafers, and after that for thicker layer it needs to be there from a very long period of time, and then we take it out and it cools down again. So what is rapid thermal processor? Do you know how we define thermal budget actually? Thermal budget is one of the very important parameters in fabrication. You always keep in mind what is the thermal budget. Anybody who can define thermal budget actually?
The temperature to which you can go after you deposit layers on the silicon substrate. Like once you do metallization, you can't go on to higher temperature processes. So once a particular layer is grown, your thermal budget keeps shrinking down. Like you've used up that much of your like you can't go beyond say 300 days.
Yes, you're right to a certain extent. Thermal budget is actually thermal budget or thermal exposure, we say. Thermal budget or thermal exposure is the amount of time for which you put a specific wafer at a certain temperature. So it means that if I have put one wafer at 1000 degrees centigrade for 1 hour, while the other wafer has been at 1000 degrees same temperature in the same furnace for 2 hours for a greater period of time. So the second wafer has got greater thermal budget because it has been exposed to 1000 degrees centigrade for a longer period of time. So the time of exposure to a certain high temperature, that is actually counting your thermal budget. That actually tells you that what is your thermal budget for this device. Okay, so the time for which you expose your device to high temperature, that defines your thermal budget or thermal exposure. So in RTP, in rapid thermal processing, what is the major benefit? That it decreased your thermal budget to a much larger extent. Why is it so? As the name tells, it's actually fast ramp process. Fast ramp means that in the wafer, generally if we put the wafer in a furnace, maybe in vertical furnace or in horizontal furnace, the temperature of the wafer increased by 10 degrees centigrade in 1 minute, approximately. And it's when it's heating up, and when you cool it down, it's even slower. So it heats up a bit faster. We'll do it tomorrow in the lab, that you will see that when we put it inside and when we take it out. When we take it out, we'll have to wait for some time so that the wafers cool down. Before that, we cannot touch the wafer because it needs to come back. So, and that's where actually the stress comes into. That's why I was telling you the residual stress. When you cool it down from high temperature and when you heat up to high temperature, due to the difference in the thermal coefficient of expansion, there would be a stress as well. Okay, so this is very slow actually. It takes much time for the wafers to heat up to 1000 degrees centigrade, and it takes much time for the wafers to cool down to the high temperature, low temperature. So that's why our thermal budget would be very high. What is in fast ramp process? That rate is actually (50 to 75 degrees centigrade in 1 second, not in minute. So in just few seconds, you heat it up to 1000 degrees centigrade. According to this, maybe in 15 seconds you can heat it up to 1000 degrees centigrade. So it means that you are exposing to the wafer exposure to 1000 degrees centigrade. Instead of 10 minutes, it's only 15 seconds for the same amount of thickness. Okay, so that's why the thermal budget decreases to a lower value. So it decreases the thermal budget, that is, decreases the wasted thermal budget due to ramp up or cool down stages. So these are the ramp up, and this is cool down stage in typical furnace. So that thermal budget is actually, I can say it's a wasted thermal budget because it's not giving me any benefit. I'm just cooling it down and I'm just heating it up to 1000. So after it reaches 1000, then my actual thermal budget comes in, the beneficial part actually comes into part. This is the wasted thermal budget range. So it actually almost eliminates, if not, I should not use eliminate, but it decreases to a very high value. So a decrease in thermal budget is the benefit that we are getting in case of RTP, that is rapid thermal processor. And in this case, you can ramp up the temperature very fastly, and similarly cool down very fastly, and in a few seconds you can heat it up to 1000 or 1100 degrees centigrade, and even you can go to high temperature in few seconds. So that's why the thermal budget decreases. At the same time, your oxidation rate increases. because you can heat it up to high temperature in few seconds. So at high temperature, the oxidation rate actually increases. We talked about yesterday that at high temperature, the oxidation rate increases. So that's why this RTP has got benefit over vertical furnace. Now, one thing that it processes a single wafer at one time. It takes a few seconds, but this RTP equipment, it processes a single wafer at one time. A single wafer goes in, and at that high temperature, it's kept for a certain time, and then the next wafer comes in. So, in terms of throughput, because it takes very small time, that's why its throughput is even greater than the vertical furnace. But if it would have taken a large time, as in case of furnace, then the throughput would have gone very low. But due to smaller time, the throughput is not affected that much. But this is a single wafer processing, so it means that it's a more controlled process, because you are working on a single wafer every time. And usually we use the tungsten halogen lamps to heat up that rapid thermal processor. So the graph shows that rapidly it actually heats up, and then at that specific high temperature it's maintained for a certain time, and then rapidly it actually cools down as well. So in typical furnace, the ramp up process or the cool down process is very sluggish as compared to RTP. Okay, so that was all about the oxidation systems. We talked about horizontal, vertical furnaces, and we talked about RTP, that is the rapid thermal processing. And now we will talk about that how to measure the thickness of oxide. How we can measure the thickness of oxide. So the thickness of oxide, the measurement of the thickness of oxide is very important, as you know this thing that if I want to etch, or if I want to pattern something, pattern the silicon dioxide, I should know about the etch rate and the thickness of the oxide. Exactly what is the thickness of the oxide until I don't have an etch stop, and exactly what is the etch rate of that etchant is. So in order to measure the thickness of the oxide, there are different methods that can be used. One is the optical method, optical measurement. The other one, it may be the electrical measurement, and the third one, it may be the mechanical or the physical measurement. Mechanically or physically, you measure what is the thickness, or electrically, you know that you can measure the capacitance of that oxide layer. It can give you the thickness. We'll talk about that as well. So first of all, that optical measurement. Optical measurement is one of the most widely used measurement that is used to measure the thickness of the oxide. In optical measurement, one way is to measure the optical interference, is to make use of the optical interference. In that case, what happens that if you exactly know what is the coefficient of refraction for that, the coefficient of refraction, you know that. If you know that what is the coefficient of refraction for the specific oxide layer, you know that for that oxide layer, the process and the conditions by which you have grown that oxide, it will change your refraction of coefficient. Okay, so you should exactly know that what is the coefficient of refraction for your oxide layer, and then you can use this optical interference method to find out what is the thickness, oxide thickness. As the formula shows you, that X oxide can be used by lambda, that is actually the wavelength, G, that is the order of interference, and after that Ni, that is the index of refraction of oxide. So approximately it's 1.46 at the visible wavelength. How it actually works, that if you have the oxide layer, light comes in, and after that it is reflected from the upper and the lower interfaces. Actually, the upper interface is air and silicon dioxide, and the lower interface is silicon dioxide and silicon. Okay, so both these interfaces actually reflect that light, and that reflected light actually will interfere with each other. So the interference will let you know what is the thickness. You got my point? What I'm talking about? The two interfaces. This is silicon and this is silicon dioxide and this is air. So if light comes in, it is reflected from this surface, one way. Secondly, it should bend down because it's 1.46 more than 1, and it's reflected from this surface as well. So these two reflected waves actually interfere with each other. So depending upon this thickness, because this is actually the additional distance that this wave has traveled. This is the additional distance that this wave has traveled. So depending upon the and this additional thickness is actually, it's actually related to the thickness of the oxide. So the thicker the oxide, the more distances needs to go in. So it means that first order, second order, third order, we will be having constructive interferences, we will be having the destructive interference as well. So we are interested in destructive interference in here, because in that destructive interference comes into play at that's why you may see that G is equal to M plus 1 by 2, where M is equal to 1, 2, 3, 4. So that's why at these values of M, we have. Sorry, my battery is going down. Okay. So in this case, we measure the destructive interference that at what wave at what value the destructive interference comes into play, and that will give us, by putting in that value, that will give us what is the thickness of the oxide. So using interference relationship to find oxide thickness, and the next method, that is actually the ellipsometry. This is also the optical measurement, because it also uses some optical instrument or optical phenomena to measure the thickness of the oxide, and this is what we'll be doing in the lab tomorrow. Ellipsometry. We will measure the thickness of the oxide by using an ellipsometer. Now in this case, even if you don't know the index of refraction, even if you don't know the index of refraction of the oxide layer, you can measure the thickness, because it permits you, tomorrow I'll demonstrate to you as well, that we can find the index of refraction of the particular layer of oxide that we are growing. And as I told you, it would be approximately in the range of 1.46, but it can vary a little bit depending upon the process conditions, depending upon the condition of the oxide under which we are growing that oxide. Okay, so in ellipsometry, what happens? Phenomena is actually the same, that you have the wafer surface, and at certain specific incident angle, that incident angle is fixed actually. In our case, it's 70 degree in the ellipsometer that we are using in the lab. That is, at the incident angle is fixed, and the light comes in, and it again reflects from the surface of oxide, and it is detected by the detector on the other end. So as in the diagram you can see, it's almost the same diagram, and after that it manipulates. There is a software. That's why we say that it's the microprocessor control way, because you need a computer. You can see a computer screen there. So on the computer screen, you will find out that what is the thickness of the oxide layer that you are having on the silicon surface. Now how it actually works, it actually takes into account the change of state of polarization of light when it is reflected from the surface. So the light comes in and it's reflected from the surface. So due to the, one thing that is necessary for this, it should be a transparent layer that you can measure the thickness in. So due to the reflection, the state of polarization that changes, and the extent to which that state of polarization changes, that is detected by the detector, and the extent of the change actually calculates towards what is the thickness of the oxide that we have on that wafer. Okay, so the light that is the angle the incident angle that we are using, that is 70 in the lab, and the light that would be striking, that would be the laser light. The laser light actually strikes in, and after that, due to the change of state of polarization, the detector detects it and it manipulates by the microprocessor inside the computer, and you will get that what is the thickness that is being made by the ellipsometer. Okay, the third thing that is that would also come under the optical measurement, because due to the constructive and destructive interference of light, you will see a different color of oxide. And this thing we will experience inside the lab as well. That after every thickness, you will see that for the first few hundred angstroms, you won't see this thing for the first few hundred angstroms. That's why it is starting from 500 angstroms. Okay, so I would say after 700 angstroms or 600 angstroms, you will clearly see that there is a color change in the wafer. When thick and thick oxide comes in, that color change goes changing, and that you can see for 1200 there is royal blue for that 1200. So in our wafer, mostly that is for 1500 there is light blue to metallic blue. So mostly in our case, our wafers would be having this much thickness, 1200 to 1500 angstroms finally. So finally the wafer should have this color, that is light blue or royal blue. So you will see that after the end of the oxidation experiment in the lab, your wafers, initially they were gray because it was silicon only, and at the end you will see they are blue. Due to the oxide, they are royal blue or light blue, just like sky blue something. So that is because it means that it's having a thickness of 1200 to 1500 angstroms of oxide. Okay, you can see that the blue color actually due to the oxide thickness, and this is as I told you that physically or mechanically you can measure the thickness as well. If you exactly want to measure the thickness, then you should use this thing, because it gives you the accurate thickness of your oxide or some other layer. It may be any layer. So in that case, what you need a step height. It means that we need to mask a certain part of the wafer from getting oxidized, and after the oxidation process is over, there would be a step height like this. For example, that this is silicon, and by some masking or any process, I could manage to get this part of silicon not to get oxidized. So this part of silicon is not oxidized, this part of silicon is having the oxide layer. So here is that step that I have. So by using the profilometer actually goes along the surface. So it goes along the surface. So when there is a jump, it will give you that there is a jump. So it actually plots the topography. So when it gives you in this way, this is the topography. So you can find it, okay, this is the thickness of my oxide. But in order to, you know that it's more difficult, because one thing, you should be able to have a clear step height. Means it should not be like this, that maybe you could not manage to save this silicon layer from getting oxidized. If it is getting oxidized, the answer would not be accurate. And secondly, mechanically you need to do this thing, so you should exactly know that where the step height is. If you don't know where the step height is, you won't be able. If I don't know that at this point the step height should give me the silicon dioxide thickness, so I cannot use the profilometer. So that's why it makes the process a bit complicated, because you are doing it manually, but it gives you the very accurate answer. So that is physical method. So you can see that if you have got a step height, so this is the tip of the profilometer, so it actually goes along this, and when it sees a step height, so it actually gives you the topography that there is a step down, so that step height gives you the thickness of the oxide layer. Okay, as I told you that we can measure the oxide thickness by electrical measurement as well. We have discussed physical, we have discussed optical, and this is the electrical. In electrical, what you can do, measure the capacitance. So if you know the capacitance, you can find out the thickness by using that formula. So X oxide or T oxide is mostly used for denoting the oxide thickness. So oxide thickness is denoted by T oxide. So T oxide is always equal to C oxide. This A is actually the area of your capacitor divided by epsilon oxide, epsilon naught. Epsilon naught is the permittivity of air, and epsilon naught is actually the permittivity of your oxide layer. Okay, so E oxide and epsilon naught, their fixed area is always fixed if you know that what is the area of your oxide, area of your capacitor actually. So keep in mind that we will be using this equation. We will be using this equation in our lab, because as I told you that the final experiment that we'll be doing on that wafer, that would be the MOS capacitor. We will have to fabricate the MOS capacitor, and by using them, that when you fabricate the MOS capacitor, you will be able to find out what is the capacitance C oxide. Okay, so once you know the C oxide, you can find out the thickness, or if you know the thickness, you can find out the C oxide. So in the lab, what we will do, that by using the same formula, I told you that area, you should know about the area. Area depends on that what is the structure of the capacitor that you have. If this is a capacitor, you should know about the diameter. This capacitor would be having, it has different capacitance, it has different capacitance value because the area is different. Make sense? Its area is different because its diameter is different. So this is what we are going to do in the lab. We will be having capacitors of different size. So we will measure two different sizes, and we will see that the capacitance is different for this capacitor, and the capacitance measurement is different for this capacitor. So when you measure C oxide, this is what we will measure in the last lab. You know about T oxide because in the first experiment you will be measuring the thickness of the oxide. So when you know the oxide, you can calculate C oxide as well, right? You can calculate your oxide capacitance if you know about the thickness of the oxide. If you know about the thickness of the oxide, you know about the area of your capacitor, and these two values are constant. So in that case, you can calculate the C oxide. So this is how you will analyze. This is a measured value, and this is the calculated value.
I think this equation is quite different from the general capacitance equation. Like C equals, we know that C equals epsilon A by D or X, whatever.
Mm-hmm.
It seems like otherwise, like X is at the numerator, A is in the denominator.
When we'll be doing that experiment, I'll explain you that these are actually the same thing. Maybe the units are different. I'll let you know. Okay, so it means that if you know the capacitance, you can measure the thickness electrically as well. So in order to measure the thickness of the oxide electrically, you should measure the capacitance of that oxide layer. Okay, now the gate oxidation. We know this thing that we use the gate oxide in most FETs, and in that case, the next slide should show it actually. In that case, actually, what we do that we etch the oxide layer. In the gate oxide, we etch that oxide layer, but that oxide layer is due to the etching process, that oxide layer, because it is over etched, that is not very accurate, so we need to deposit the polysilicon again. But make sure that it should be very optimized process actually, because we deposit the polysilicon again, so it may happen that you have over deposited the polysilicon. So in case of gate oxide, it should be a very optimized process, because your etching process and your deposition process, that needs to be very specific. This is actually the important slide that I need to discuss. That is, you may have heard about LOCUS, LOCUS, that is local oxidation of silicon. That is very important in case of MOS FETs. So what you actually need to have, you know that this is the field oxide and these are the active areas. Okay, this is how it looks like. Your MOS FET, it looks like this. In the middle you have got the field oxide, and the active area you've got thin oxide layer. So this is the gate oxide. So one thing for your knowledge, that gate oxide is mostly grown in dry oxidation, and because it's thin. And field oxide, if it's not told you that whether we are using the wet oxidation or dry oxidation, so always go for the wet oxidation parameters. Always use the wet oxidation parameters, because field oxide is always a thick layer. So in this case, you can see that first of all what I did, that I patterned my oxide layer, and after that I put the nitride layer as a passivation layer, or as a photomasking, as a mask, hard mask. After that, I thermally grow the oxide. When I thermally grow the oxide, you know this thing that it will grow. It goes under the silicon nitride layer as well, under the nitride layer. So so what it will do is, if the height of that oxide is too much, it's because the growth is always two-dimensional. It's not growing in this way. It's also growing in this way. Due to the two-dimensional, the height increases in this part. The height increases, but at the same time, it increases this way as well. It goes under the nitride layer. So when you move the nitride layer, you will see that you have this shape, and due to this shape, we call it as bird's beak, because it's like a bird's beak. So that's why we call it as bird's beak, that actually encroaches under the nitride layer. So it means, the important point here is that if I need to grow 500 nanometer, if I need to grow 500 nanometer of oxide, this is 1 micron, 1 micrometer. These are my active areas, right? These are my active areas, and this is 1 micrometer. Now I want to grow 500 nanometer of oxide in my field oxide, in that pad oxide layer. So when 500 micron is grown here, so means there would be this beak as well. Bird's beak would be there. Okay, so bird's beak encroaches inside. So that bird's beak means the lateral growth, that would also be 500 nanometer. If 500 nanometer in this way, 500 nanometer in this way. So what does that mean? From this end, 500 nanometer comes in, from this end 500 nanometer comes in. So it means the active area, there is no more active area. You lose your active area. So it means that in case of bird's beak, the active area should be larger. I need to make sure that my active area is large enough that due to the bird's beak, the active area does not disappears, because that bird's beak encroaches from both sides. So active area should be at least 2 times the thickness of the field oxide, at least more than 2 times the thickness of the field oxide, so that the field oxide is 500, it encroaches 500 from this side, 500 nanometer from this side. If it's 1 micrometer, so it means nothing left. 1 micrometer is equal to 2 times of field oxide thickness, so it means there would be no active area. So my active area should be large enough. Maybe we have not mentioned on this slide, but the active area should be large to avoid this blockers. So this is the last thing, that is shallow trench. One other method that is used to avoid that bird's beak, that is shallow trench isolation. In this case, what we do, as you can see from here, first of all we drill a trench. After that we etch this oxide, the underneath oxide, pad oxide, under etching. After under etching we grow. Here we are growing the oxide layer, and after growing, what we do? CVD, chemical vapor deposition of oxide. So here we deposit, we don't grow, here we deposit. Actually you can see, that is, if we need a thicker layer, we can deposit. So we deposit that oxide layer, and then chemical polishing, and then we actually remove our nitride. So in this case you can see that we can have a thick field oxide as compared to my active area, that is the gate oxide. So this is a good approach to have a thicker field oxide as compared to my gate oxide, that is shallow trench. You get a trench, and after that you under etch that oxide layer, and then you deposit. After deposit means that that trench actually fills up with the deposited silicon dioxide, so you have a thicker layer of oxide in the middle. You don't have anything at the other side, because the growth actually grows in both ways. Deposition will deposit on everywhere, so just like a blanket deposition in the hole, you will be having a thick layer of oxide. Thermal oxides, these are, we have already discussed that etch hard mask, ion implantation screens, sacrificial layers, capacitor dielectric. So these are different benefits of the oxide layer, different uses of oxide layer that we have already discussed in the last lecture. As I told you that we are trying to seek out the alternatives to silicon dioxide, but any alternative to silicon dioxide should be having a high dielectric as compared to silicon. So we are interested in the materials, in the layers that have high dielectric. Silicon nitride is the second option, but there are some other options as well, like titanium oxide. Okay, this is the equation that is used to find out the equivalent thickness of the alternative oxide layer if we have some other oxide layer. So by using this thickness we can find out what is the equivalent thickness. So limitation of silicon dioxide, as the limitation is that we cannot grow very thin layer. We don't have a better control of very thin layer of oxide. Very thin layer of oxide cannot be better controlled, because in order to grow a thin layer we decrease the pressure. At low pressure we try to control it, but still we cannot go beyond 1.5 nanometer. And as the scaling chart says that after 2014 we should be having 0.6 micrometer thick layer, or nanometer, 0.6 nanometer thick layer of oxide. So that